Okay, welcome to the lesson on energy stored in a spring. You've done some work on what we call Hooke's law, which is relating the force and the spring constant and the extension of a spring. So we're going to use a little bit of that today, but we're going to look at an equation which you don't need to learn. It's given on the formula sheet. You're going to look at an equation for working out the energy stored. First of all, we're just going to look at the energy changes in systems involving springs. Then we'll investigate how the energy stored in the spring can propel objects at different distances. And I'm going to remind you of a practical you've done in lesson. And then at the end, we'll apply the equation and we'll calculate some energy stored in a spring. First up, it's a bit silly, strange, extreme video. Let's look at some energy changes in the spring. So if I just flick to this video, we'll see we've got this person who's sort of boinging down the road and they're doing backflips. So you can see they're going all the way over, and they're doing that by compressing a spring using their weight and then bouncing up, doing a somersault and then flipping over. And I think they come back and announce that they've done 9 or something like that, 8 or 9. So if we just watch it again in slow motion, you can see the spring compresses, and then as it expands, it forces the person to do a somersault. And just really quickly, I want to just look at what are the energy changes going on. So if we just go back to the slide here, describe the energy changes in a spring as the man does a single backflip. Think about energy at the lowest point, just as they leave the ground, at the highest point, and as they touches the ground again. Well, at the lowest point, the spring is compressed, so we would say that the spring has stored all elastic potential energy. And then just as a person leaves the ground, the spring is uncompressed, so all of the energy is being converted into kinetic energy because that person's on the move. And at the highest point, all of the kinetic energy is being converted to gravitational potential energy, and they've got as high as they can, and then they start to fall back down towards the earth again, and just as they touch the ground, all of the gravitational potential energy has gone back into kinetic, and then the cycle starts all over again. And just to get you thinking, why do you need a road to do this on and not a field? Try to explain in terms of energy. And of course, if this was a field, then instead of the spring compressing, it wouldn't squash because the end of the pogo stick would end up going into the ground and deforming the ground. And of course, the ground won't spring back. The ground doesn't store the elastic potential energy like a spring would. So most of the energy will be transformed in deforming the ground or changing the shape of the ground, and you wouldn't be able to get it back, so it wouldn't get converted into kinetic, so the person wouldn't be able to do it. Okay, so that's just a little bit of an idea of where we're going with this, but we need to put some numbers on this. And in the classroom, in the lab, you should remember doing this practical, and this was 2 pieces of wood with 2 springs, and what we did, we compressed the springs by squashing it with our fingers, and then we placed in front of it a circular mass, a 100-gram mass, and we let it go and let the mass fly across the desk. And what we did, we measured the distance travelled. So if I just go back onto this distance here will be the distance that the spring is squashed. So you can see that squashed that far, and then we ping the mass across the desk and we measured the total distance that the mass actually moved. And you did it for different compressions of the spring. So these are our compressions, or I've just labelled it extension because that's what we used to calling it. But remember, some springs can be extended or compressed. So we've squashed it by 5 millimeters, and we see how far, then 10, then 15. And I'm not going to go into the results because I'm not too fussed about that at this stage. All I want to quickly mention is that if we plotted distance against extension, then if this was a proportional relationship, we check this because this would be a straight line through the origin if it's proportional. So as you double the distance, you would double as you doubled the extension, you would double the distance. It's not actually, and that's because the relationship is to do with a squared value, but we're going to come to that in the formula in a moment. All right, so that's just a little bit of a memory as how you tested the energy stored in a spring. So the formula, again, I've got across the bottom of the screen. You just need to be able to use this equation. You don't need to be able to remember it. The energy stored is this. It's half times the spring constant times the extension squared. So the letters are E equals half KE squared. Some quick notes: the energies, to get the answer in joules, then you need to plug the numbers in meters. So the extension's got to be meters and the spring constant's got to be newtons per meter. Alright, so very quick example. A spring with a spring constant of 25 newtons per meter is stretched, so the length of the spring increases by 0.1 meters. How much energy is stored? So using our formula, let's plug some numbers in. Half the spring constant times the extension squared. If you put all that in your calculator, you'll get an energy stored of 0.125 joules. Okay, so we could do some slightly more difficult ones. Well, we'll start off with some easier. A spring with a spring constant of 30 newton meters is stretched, so the length of the spring increases by 0.2. How much energy is stored? Again, half 30 times 0.2 squared. Into your calculator, you get an answer of 0.6 joules. Remember, when you're using your calculator, you put 0.5 times 30 times 0.2 squared. You just square the 0.2. You don't square the whole answer. It's just the extension squared. Okay, another one. A spring is stretched with a force of 300 newtons and its length increases by 10 centimeters. How much energy is stored if it is stretched to 20 centimeters? So the first thing we've got to do here is we don't know the spring constant, so let's work it out. We've got 300 newton force increases it by 10 centimeters. So using our formula from last lesson, F equals K times E, force equals spring constant times the extension. Rearrange to K equals F over E, plug some numbers in. K equals 300 divided by 0.1. which gives us an answer of 3,000 newtons per metre. If you're thinking, where's 0.1 come from? Well, I've converted 10 centimetres into metres, so 10 centimetres is 0.1 metres. Now we've got a value for K, we can use our half KE squared. So let's plug the numbers in. Half times 3,000, which is K we've just worked out over here, multiplied by the extension here of 20 centimetres converted to metres is 0.2, and I square it, and if I put all that in my calculator, I get an answer of 60 joules. So again, while you're watching this, if you can, please try and check and use your own calculator. Now, things might not be always that simple, and I've got a warning here, be careful. Using the formula, if you're working out the energy stored between two extensions, you are not starting from an unstretched spring. So remember, this extension is always the actual individual extension. If you extend it, and then you extend it again, you can't just use the change in extension and square it. I've put on the next line. You need to work out the two energies and then take them away. So what do I mean by that? Let's have a look at a question. A spring of spring constant of 100 newtons per metre is stretched so the extension of the spring increases from 0.5 to 0.8. How much extra energy is stored? Now, what you might be tempted to do is use the formula and put the extension in as 0.3, which is the difference between these two, but you can't do that. You have to work out the energy stored here and the energy stored here and then take the two away. So the energy stored at 0.5 metres is half KE squared, half 100 times 0.5 squared. The energy stored at 0.5 metres is 12.5. Then you do exactly the same for 0.8, half KE squared, half 100 times 0.8 squared. Energy stored is 32. So going from 0.5 to 0.8, you would say it's 32 minus 12.5. So 32 minus 12.5 will give you an answer of 19.5 joules. Okay, so that's when the questions get a little bit harder. They might test you to make sure you're up to your maths is up to this, and you appreciate that you can't just do the difference between the two extensions. So let's just finish on a couple of harder questions then. A spring of spring constant 50 newtons per metre is stretched so the extension of the spring increases from 0.3 to 0.6. How much extra energy is stored in it? So here we go. The energy stored at 0.3, half the spring constant times 0.3 squared is that. Then let's do 0.6, half the spring constant times that extension, 0.6 squared is 9, and then we do 9 minus 2.25 to give us an answer of 6.75 joules. And then finally, a spring of original length 40 centimetres needs a force of 80 newtons to change its length to 45 centimetres. If it was then stretched so its length is now 55, how much energy is stored? And again, you might notice in this we haven't got the spring constant, so we've got to work it out. So force is spring constant times extension, rearranged. Spring constant is force divided by extension, and we've got a force of 80 gives an extension from 40 to 45. I nearly got myself confused there. So 80 newtons goes from an original length of 40 to a new length of 45. So that's an extension of 5 centimetres. So 5 centimetres in metres is 0.05. So I'll do force of 80 divided by 0.05. So we've got a spring constant of 1,600 newtons per metre. Now we can use the formula that the energy stored is half the spring constant just calculated times the extension squared. And if you look, if it was then stretched so its length is now 55, so going from 40 to 55, it's now 15 centimetres, and 15 centimetres in metres is 0.15. So I've got an extension here of 0.15, so I can put that all in my calculator and I get a final answer of 18 joules. So the questions might test to see if you can work out the spring constant and then use it in a calculation.